name's Ricardo Vidrio, working in the Stucky Lab under the mentorship of Dr. Young C. Jun. And I'll be talking about lithium-air batteries today and the search for better electrocatalysts. So if you were to take every battery on Earth and combine them all together, that super battery can only power the world's energy needs for about 10 minutes. So just by saying that and the evidence provided in this graph right here, we can see that today's modern batteries, the most that we use, such as lithium-ion here, they don't really supply a lot of energy, and they're insufficient enough to meet our growing energy needs. So here at UCSB, we're trying to make a battery that can rival fossil fuels, as we see up here. So the green bars here, they represent theoretical energy density. That's pretty much energy density that we could have. And the blue bars represent a practical energy density. It's energy density that we already have. So our job here is to make lithium-air rival gasoline by turning it into practical energy density. So let's get into the mechanics of how the miracle battery works. So before I get into this, let me just explain a couple of components here. So over here we see a solvent electrolyte / tech DME. All that really is the way through which these electrons are all flowing, and the tech DME stands for tetraethylene glycol dimethyl ether. And we can see that this whole reaction, this whole battery works because of that reaction that's up there. The thing that's driving these electrons forward and backwards is just a simple redox reaction that most of us learn in any Gen Chem class. So on one side we have the lithium, which is the anode side of the battery, and on the other side we have the cathode side of the battery, which is where the O2 comes in. Something of importance here is that on the cathode side of the battery, there needs to be a steady stream of oxygen coming in, which is why we close off our batteries in this beaker-type container that I'll show right now. So how this usually works is on one side we have lithium ions flowing across the entire electrolyte, going to the other side of the cathode, and producing our lithium peroxide, Li2O2. So the purpose of that electrolyte salt right there is to better help dissociate the lithium ions. We want to break the lithium ion guys apart so that they'll get to the other side and make our lithium peroxide. As long as we're making lithium peroxide round the clock, we'll know that this battery is running at full efficiency. So let's get into the problems that we're having right now. So the problems that we're having is, as shown here, these 5 guys right here aren't meeting up as much as we'd like them to. So this battery would work at full efficiency if we have 2 lithium ions, 2 electrons, and a radical O2 ion all meeting up at the anode, as I just showed. The problem is that this is rarely occurring. And this is pretty much a huge hindrance. Most of the problems that are occurring with lithium-air batteries, such as their poor cyclability issues, they're not discharging enough current, they're only peaking out at about a certain capacity that can't rival fossil fuel right now, goes back to this issue right here. And it's this lack of union that's really what's causing this problem. So let's take a look at how we're going to tackle this problem. So we're dealing with 2 very important aspects right here. One of them is, the most important one, as you can see by the red text, is figuring out a perfect electrocatalyst. The electrocatalyst is what will help the party of 5 get together pretty much all the time. And another thing we're pretty much dealing with is assembling these batteries on a weekly basis. We're assembling about a dozen batteries on a weekly basis, and we're analyzing their cyclability, how much energy density they're giving us, how much current they're discharging, pretty much basic battery stats. And as you can see on that graph right here, we enclose our batteries in this beaker, and inside that beaker is just a bunch of O2 gas. And you'll see right there, that's a coin cell, and that's pretty much the battery. It's about the size of a dollar coin, and you'll see the little holes right there. That's where the O2 is coming in. And that bottom side would be the cathode side of the battery. So before I delve into this, let me just explain that what makes a good electrocatalyst is if it's mesoporous, it has a high surface area dispersion. That means it's going to get all over the electrolyte and help those guys, help everything skirt across the electrolyte. And it has good ionic conductivity. It has to promote this flow of ions and electrons across the entire battery. We found that graphitic carbon nitride and titanium nitride make particularly good catalysts. Now these pictures right here, these pictures, we have spheres and rods. So So we found that these spheres and rods are particularly good catalysts, and they pretty much help promote ionic conductivity through the entire battery. And this is made through a process known as molecular cooperative assembly. It sounds complicated, but it's pretty much just a controlled synthesis of this nanostructure organization. And all that really means, goes to show, is that how we generate these catalysts, they have to come out as these spheres and rods right here. So before I explain this graph, let me explain that little square right there. So on one side we see Super P. Super P is our go-to catalyst. It's been proven time and time again that it'll increase the capacity here of pretty much any battery. So by default, any catalyst that we come up with has to be better than Super P. MCA right here, let me go back one. So we combine MCA with graphitic carbon nitride to make a pretty good superior catalyst, and that's pretty much all it is. And MCA is just melamine cyanuric acid. On the left side, we have titanium nitride. There's a lot of value in titanium nitride because currently it's being used as an anti-rust coating. So it's being, I would say, not mass-produced, but it's in fabrication right now. And if these batteries are ever to reach a practical stage in their development, titanium nitride could be used as a catalyst that's just geared up to go. So as we see right here on this graph, let me explain this vertical axis. That voltage is pretty much at the voltage that the battery seems to operate. And this capacity right here is just an energy density value that's identical to the one I showed in my first slide. So as you can see, titanium nitride is the superior catalyst because it's almost reaching the energy density of fossil fuels. A good way to think about this is the electrocatalyst acts as the holy grail for air batteries. It's the electrocatalyst, it's the fact that we don't have a good enough electrocatalysis that doesn't make these batteries viable or practical enough. Because the batteries that we have right now, say lithium-ion batteries, they don't have a high enough energy density, but that means they're really good. They have a really good cyclability. That means you can recharge them and charge them again, and they're tested and proven. And we need to get these batteries to this level. So there's still a lot of facets of experimentation that we're working on here. One of them is changing the anode side to this CaLiO2 alloy anode. And what that pretty much is that we're adding calcium to the anode side because calcium has 2 valence electrons as opposed to 1 valence electron found in lithium. And that means it promotes better ionic conductivity throughout the entire battery. Another thing we're doing is we're replacing the electrolyte salt. Recently we've upgraded to trifluoridic acid, and that pretty much just helps the dissociation of lithium work better. And we're also trying new combinations of electrocatalyst concentration. One important thing to remember is we have to add just the right amount of electrocatalyst. We can't just add like 100 milliliters or a huge amount because it might actually hinder the performance of the battery. So we have to find a good combination. As well, we have to know what cell we're working with in order so the design won't be hindered. And we're also experimenting with lithium-sulfur batteries. Now, this is particularly good because lithium-sulfur batteries don't require a high purity O2 environment to work in. It's an easier process to build them and to operate in. They don't require that beaker I just showed. So our work is far from done, but our graphs keep getting better and better with time. And I'd like to conclude my presentation by thanking Dr. Stuckey for providing me the opportunity to work in his lab, Dr. Jun for mentoring me all this summer, Erica for allowing me to be a part of UC Leads, and that concludes my presentation. Thank you.